SAMCLIP, Merging Vision Foundation Models Towards Semantic and Spatial Understanding. This is a paper from Apple and the UIUC teams. The landscape of publicly available vision models, VFMs, such as CLIP and Segment Anything Model, SAM, is expanding rapidly. VFMs are endowed with distinct capabilities stemming from their pre-training objectives. For instance, CLIP excels in semantic understanding, while SAM specializes in spatial understanding for segmentation. In this work, we introduce a simple recipe to efficiently merge VFMs into a unified model that assimilates their expertise. Our proposed method integrates multitask learning, continual learning techniques, and teacher-student distillation. This strategy entails significantly less computational cost compared to traditional multitask learning from scratch. Additionally, it only demands a small fraction of the pre-training datasets that were initially used to train individual models. By applying our method to SAM and CLIP, we derive SAMCLIP, a unified model that amalgamates the strengths of SAM and CLIP into a single backbone, making it apt for edge device applications. We show that SAMCLIP learns richer visual representations equipped with both localization and semantic features suitable for a broad range of vision tasks. SAMCLIP obtains improved performance on several head-probing tasks when compared with SAM and CLIP. We further show that SAMCLIP not only retains the foundational strengths of its precursor models, but also introduces synergistic functionalities, most notably in zero-shot semantic segmentation, where SAMCLIP establishes new state-of-the-art results on 5 benchmarks. It outperforms previous models that are specifically designed for this task by a large margin, including 6.8% and 5.9% mean IOU improvement on Pascal, VOC, and Cocoa Stuff datasets, respectively. Figure 1. Yes, thank you. SAMCLIP inherits most zero-shot capabilities of SAM, instance segmentation, and CLIP, classification, using a single shared backbone on the left. Further, SAMCLIP is capable of a new task, zero-shot semantic segmentation, and obtains state-of-the-art results on several benchmarks, with a large margin compared to previous models specifically designed for this task on the right. Detailed results in Table 1 and 2. Zero-shot semantic segmentation is a new task, and they do it better than anybody. In Figure 1, SAMCLIP is the light green area which covers nearly the whole circle. That's pretty impressive.
So SAMCLIP, green, ImageNet. So is SAMCLIP state of the art? It is.
It looks like it to me.
It is, yeah. That's nice. Zero shot instance segmentation. Oh, wow, that's pretty good.
The big drawback of SAMCLIP is that it is not an open source model. It may be that we can get enough information from this paper to be able to train an equivalent now that Meta has released their CLIP model.
That's right. What was the name for that?
Meta CLIP.
Meta CLIP. Nice.
I'd like you to move down to the top of page 4 with the training pipeline. Thank you. Up a little, yeah, that's it. Figure 2, multi-head architecture of SAM-clip. Left, the training pipeline where we perform multitask distillation from clip and SAM teacher models on dataset clip and dataset SAM datasets, respectively. They're using, let's see, they're feeding in both clip, the data set for clip and the data set for SAM into an encoder for SAM clip and a prompt encoder for the labels for the semantic segmentation. The encoder is going into a head device for clip and a separate head device for SAM, which is combined with the prompts and the labels for SAM. And then the head clip is separately run through a pooling and L-clip layer. The trainable component of this is on the left-hand side with the head clip. The SAM side is the frozen side. Did I get that right?
Yeah.
So the left,
and then
so
moving to the next one.
the
On the right, it shows our inference pipeline, where a single backbone, we can perform multiple promptable tasks, classification, instance segmentation, and semantic segmentation. The circle with the dot in it denotes inner product between text embedding and image patch embeddings. So on the inference pipeline, you feed in a label, motorbike, an image of a motorbike, and an image input geometric prompt, which has a bounding box around the motorcycle. The left-hand side is trainable, and the right-hand side is frozen. The text encoder clip spits out an image mask, which corresponds to the motorcycle against a plain background. And this is combined with the output of the SAM clip encoder, which is also run through the head clip. The bounding box motorcycle goes into the prompt encoder SAM with an output mask. And that is fed into the head of the SAM encoder with the encoder from SAM clip, and that spits out the output mask, which is not used to create the output mask on the clip head side. They're separate. There's a SAM head output mask and a separate output mask for clip head. Any questions about that?
So let's go back to the training. We have an input of an image and an image. So that's for the clip. Then for SAM, we have an image and a geometric prompt. This is then fed into a trainable encoder of SAM clip for the image. And then the image and geometric prompt are fed both into the encoder of SAM clip and a prompt encoder for SAM. Now the encoder SAM clip will then go up and be split up into the trainable head clip and the trainable head SAM. And then we also see the prompt encoder, which is frozen, go up into head SAM and then come down into LSAM. And then the head of the clip heads output will be fed into a pooling layer, which is max pooling. Then this will then be fed in. This will then be sent to L-clip. Is L-clip the? Is that just the output?
Yeah, that's just the output. for the clip side,
Okay.
which will be labels, classification.
Inference. So prompt input text gets fed into text encoder clip, which then we compute the inner product with the head clip, whose outputs were passed in by the encoder SAM clip, who's passed in by an input image. Then that gets the output mask, which is a clip head, and that's what the image looks like. The bike. So we have the input image. We're feeding in the text encoder clip into we're feeding the text encoder of clip into the head clip. Then encoder clip is then fed into head clip and head SAM. Head SAM will output the output mask SAM head. The prompt encoder will go to head SAM and output. Okay. Let's read the background. I think that's
Okay.
starting from the
So
beginning.
I was confused on my first pass through this diagram. I thought the coloring was related to frozen versus unfrozen. I now realize that coloring is related to clip versus SAM. And so I'll go back to the background. Vision language models, VLMs, such as CLIP and Align, are trained on billion-scale, often noisy text-image datasets. These models consist of modality-specific image and text encoders that produce an embedding for each modality. For a randomly sampled batch of image-text pairs, these models are trained with a contrastive objective to maximize alignment between embeddings of positive pairs of image and text. A direct application of such models in zero-shot image text retrieval or zero-shot classification via text prompts. Radford, 2021. Other works such as VILT, VLMO, and BLIP explored shared or mixed architectures between image and text modalities and enabled additional zero-shot capabilities such as visual question answering and captioning. Approaches such as LIT, IP, and BLIP2 reduce training costs of clip-like models by deploying pre-trained single modal models. This is similar to our approach in terms of harvesting knowledge of available pre-trained models. However, we focus on merging vision backbones into a unified model in a multi-modal, multi-encoder setup. Further, on top of representation learning abilities, we transfer zero-shot capabilities of the pre-trained models. And the segment anything model, SAM, introduces a large-scale dataset, a model, and a training recipe to enable segmentation given a prompt. The dataset consists of triples of an image, a geometric prompt, and a segmentation mask. SAM consists of an image encoder, a prompt encoder, and a mask decoder. SAM's image encoder is a VIT-DET, pre-trained with MAA objective, which is endowed with a rich high-frequency localization knowledge. Prompt encoder gets a geometric input in the form of points, mask region, or bounding boxes. Mask decoder gets output of both encoders and produces high-resolution segmentation mask. SAM is trained supervised using a linear combination of focal and dice losses and is capable of generating segmentation masks even when the input prompt is ambiguous or low quality. It is noteworthy that Krylov et al. 2023 briefly discusses a possible multitask pre-training strategy to enable freeform text-to-mask capability, but has not released the model. So they may not be the only people doing this. Knowledge distillation, KD, was originally proposed to train a compressed classifier student using knowledge accumulated in a pre-trained large model teacher. Related to our work, recent works explored distillation models for VLMs such as EVA, DIME-FM, clipping, and ClipKD. They show transfer of the same zero-shot capability as the teacher model to the student. Here, a multitask setup we perform, distillation and self-distillation, and demonstrate transfer of different zero-shot capabilities from two teachers into a single model, as well as emergence of new zero-shot capabilities specific to the student model. Continual learning, CL. Our setup is also related to continual learning, where new knowledge is added to an existing model. The main challenge in continual learning is catastrophic forgetting. McClelland et al. 1995, McCloskey and Cohen 1989, referring to a loss of previously learned knowledge due to learning new tasks. Continual learning algorithms usually alleviate forgetting via regularization, experience replay, regularized replay, dynamic expansion, and optimization-based methods. Among them, replay-based methods prove to be simple yet very successful ones. In this work, we propose a simple recipe based on memory replay and distillation to merge VFMs with minimal forgetting. That's interesting. The zero-shot semantic segmentation task aims to predict a dense segmentation mask given a text prompt in an open form without prior knowledge of specific object classes of interest or any fine-tuning. Recent approaches to open vocabulary segmentation deploy image, text pairs, datasets, and pre-trained VLMs such as CLIP and their internal representations to obtain dense segmentation masks. For example, group VIT, VUCO, ClipPy, VIL-SEG, VS, TCL, and SegClip. In this work, we do not directly use any text data. Instead, all text semantic knowledge is derived from a pre-trained clip. An alternative approach is to deploy existing models without any training and generate segmentation masks using multiple backbones in a multi-stage setup. For example, one could run SAM to get several object proposals and run each through CLIP for semantic classification. Some recent works use internal attention masks of conditional vision generative models such as Stable Diffusion to obtain the segmentation mask. While these approaches are training free, they require several stages with complex processing, multiple vision encoders, and many forward passes, make their deployment for edge devices limited. Merging model techniques aim to combine the capability of different models by simple interpolation operations such as weight averaging and task arithmetic. Recently, there's abundance of such techniques, and they list about 6 papers, employing different weight schemes and parameter sensitivity and importance. The way we train SAM-CLIP can be regarded as a data-dependent merging approach, where the knowledge of the models is combined by repeatedly reminding them of their original behavior via replay, while the optimization algorithm is exploring the parameter space to find an optimum. Any questions on the tasks they're attempting to?
Zach, what do you think?
Most of it goes over my head.
V, what do you think?
Nah, I have nothing to say, man.
There's a lot of keywords here. Encoders, forward passes. And they're literally what they sound like. It's not like they're not. anything special. They encode some form of data, and they just pass something forward. A forward, like when they talk about forward passes, they are literally just passing something forward. Um, they're just applying a bunch of gradients, tensor operations, and then they're just passing those through. They're not like it's not. It's exactly what it sounds like.
I also find it quite interesting that their inference model is small enough to be run on an edge device like a phone.
Yeah, I'm actually looking at the code. Like I'm trying to like think together like how I could build this without Yeah, I'm trying to I'm looking at the code of segment anything now.
This is not open source, right?
No, I don't think.
This particular model is not, but I think we have a decent clip model with meta clips released today. That is, meta reinvented the clip model, which everybody's been using without knowing what was in it. And I think there may be a good open source SAM model, if I'm not remembering. I think there's a good one.
SAM is open source.
So this is a replicable paper.
Yeah, it is. Yeah, I'm looking at the Metaclip now. I wonder if it's any better than the original.
I'm assuming that they're going to be aiming for about as good as Clip, but probably not better. Also, it looks like the training for SAM Clip is not that expensive because they're merely combining two existing models. They're not starting from.
Why do you say that?
They're combining two models and they're combining two models and encoding with an encoder, then heading out with the head clip and head SAM. They're again like separating the clip and the SAM.
Yeah, so a little later on, there's a section where they describe the model architecture, and then they describe what the heads mean. Basically, they're taking a select amount of the transformer blocks of clip, and that's what head means in this context. They're just
I do understand.
So like a lightweight clip head, what you see there is just 3 transformer layers, or that's what they're talking about when they mean clip. And so basically, the transformer layers are just like computing the attention over the input, which is the image. So
and
SAM is they talk about what SAM is. There's an image encoder, there's a prompt encoder, and there's a mask decoder. So there's these 3 things, and that's what they're like when they talk about an encoder for SAM or prompt encoder. That's what they're talking about. They're just talking about there's literally 3 pieces. Here, I'll share my screen so I could show you what the code actually looks like. So here's like the main file for SAM. Basically, you have like SAM has an image encoder which takes in these parameters. So the image encoder here is a VIP model. It's a vision transformer, kind of like if GPT-4 was just for vision, and it's probably what it's using for vision. So you have a vision encoder, then you have a prompt encoder, and this is taking in the prompt. This is like a transformer model. So this is like GPT-4, if you will. So if we go to here, we check out prompt encoder. Let's see what this looks like. So the prompt encoder here will basically return. Where is it? So the prompt encoder here is going to return a sparse embedding and a dense embedding. And so these are going to be the embeddings of the text. Basically, when they're talking about a prompt encoder, what they're doing is just they're transforming the tokens into embeddings so that the embeddings can then be fed into the actual model, which is the transformer. Um, so that's
Interesting.
this is like the code representation of like what they're talking about in that figure. Where is it? Where is it? Where is it? So yeah, like here they have here they talk about the prompt encoder. So this is the prompt. The like this prompt here is going to be fed into the prompt encoder. Then the output of this is going to get fed into the three transformer blocks of SAM, and then this is going to output is that the loss? I think that's loss, right? Right, everyone?
Yeah, I guess that's loss.
I think that's loss. Then here we have the clip pooling to show the max pooling. Let's show the max pooling. So basically, let's see if there's a visualization of this. Basically, max pooling is a layer that enables a model to understand the spatial significance of information. Let's watch this.
That was very ultra softy.
So basically, what this is doing, the max pull is like literally pulling certain sections of the feature map or the matrix into a very small set of features. So it's basically like distillation, if you will. It's taking in. Actually, let's go to this video. Do you understand this? So basically,
Yep.
you have a matrix, then you have a stride that's basically wait. So a two by two, basically like whatever the stride is, it's gonna be
stride is a 2 by 2.
it's gonna be a square. So if you say 10, it'll be 100. So
Yeah.
then that'll go over each section, each 100, or whatever the stride is, to the second to the second power to over the matrix, and then it will get the max of each stride quadrant.
Yeah.
So this is like quadrants. Then
It's
it just takes the max.
Matrix. Right?
No, it's
I mean,
max.
if you have like that's like 6 by 6, or if you have like 10 by 5, then it that can be right. I mean,
Maybe.
that can be used. Sure, maybe it can be only used in equal number of matrices, like 6 by 6, or equal number of n by n.
Interesting.
Yeah.
Hold on to that thought for a sec. Zach, did you learn something from this?
Yeah.
What do you think?
Go ahead, Evan.
What was that?
So max pooling is a very simple compression technique.
Yep.
Also, and so we're just allowing the strongest signal to percolate through the compression. Is that correct?
Wait, what did you say, Evelyn?
So I think I would summarize max pooling as a compression technique, where it carries through the strongest signal in any one of these patches it looks at, all the way through till the final, most compressed version of it, because it's always carrying the maximum value through till the end. Does that sound correct?
I mean, maybe. Basically, max pooling, what it does, it just like it literally just like kind of compresses stuff. It just compresses stuff. Actually, let's see.
Did you understand that?
Yeah. If we just compress instead of getting the max value of any matrix, essentially.
Yes. So here's an example. So here we have a tensor of. Wait, did I do that correct? So here we have a max pooling layer. Let's just do it again. Max pool equals max pool 2D. We specify the size, which is 3, stride 2. Then we apply then we just get an input. We're going to make a 4-dimensional input, which is an image. Images will most likely always be 4-dimensional. So 20 is 1 dimension, 16 1 dimension, 50, 30. These are 4 dimensions. So then we would have, we would apply like this. Oh, I didn't spell that right. See if that works. Yeah, so let's print the original inputs. Yeah, so you see this is the original matrices before we apply max. Like, look at some of the digits. They're kind of like all over the place. They're like -3, -9. We have like 7, -7, 1.67 e minus 0.1. But then when we apply max pooling, look at them. They're like 1, 0, like 0.9403. Are you seeing this?
Yeah.
So that's like kind of like the intermediate result of max pool. Also, you could also, when you apply an operation in PyTorch, you could see the shape if you do dot shape. So if I say dot shape on the output tensor, we could see the shape of it. So it's going to be 20, 16, 24. You see this is almost split in half. And this one too. That's because of the max pool. But if we see the original input shape, look, 20, 16, 50, 32. But then if we go back to the output, well, the first two remain the same, but then this is split in half because of the max pool, and so is this dimension.
Why did the first two remain the same?
That's a good question. Why did they remain the same? Because those are related to like there's channels. There's n channels, height, and width. So we're just taking the n and the c are completely untouched, and we're just manipulating the height and width.
Okay, what if we do stride 3?
Do stride 3? So you see, it went down to a third.
More than
it went down to
third.
Yeah, it went down to a third.
Yeah, so basically stride is like the dividing part. It's like the compression factor.
Yeah. Why do the first two dimensions of the tensor remain untouched, but the last two, 50 and 32, are manipulated?
Because it's a square, man. It's a 2D, so only height and width are manipulated. Max pool 2D. It's a 2D, 2-dimension. I don't know why, but like, I mean, that was the basic answer for that. But what is N and C, by the way? Yeah, see, batch. Wait, come down. We have batch dimensions and the input channel dimension. What's batch dimension and input channel dimension?
It's just a dimension. The first two dimensions of the tensor N and C represent the batch size and the number of input channels. So the input channels are pretty common. They're basically like found in almost any like image classification. Like every vision model takes in channels. These dimensions remain untouched because the pooling operation is applied independently to each channel of each sample in the batch. The last two dimensions, H and W, represent the height and width of the input feature map. These dimensions are manipulated because the max pool operation with the specified kernel stride. The kernel size defines the size of the window with which the maximum value is calculated. It can be a single integer or a square value, or a tuple of two integers. The window slides over the input feature map, computing the maximum value within each window. The stride determines the step size of the window as it slides over the input. It could be a single integer or a tuple of two integers. The pooling operation is applied every stride, resulting in a downsampled output feature map. The padding parameter controls the implicit negative infinity padding to be applied on both sides of the feature map. And those are just some other parameters. So the shape of the output tensor depends on the input shape of the pooling parameters. For the batch dimension N and the input channel dimension C, the output channel shape remains the same as the input shape. The output height, H out, and width are computed based on the formula provided in the documentation. A 2D max pool operation is performed. The first example uses a square window of size 3 and a stride of 2. Yeah. So that's pooling. basically pooling is very necessary for just like you said, downsampling the number of features you have. Um, it's like it's basically a compression algorithm of the information inside of an image. Um, and the what is it? The inner products. Let's look at that inner product. So the inner product is different from the dot product, or not really. But basically, like um, so the thing is with linear algebra. Um, the thing is with linear algebra, everything that we see here, like all these numbers, they're not just numbers. They exist in some space. So you can
Of course
visualize.
they exist.
You can visualize them if you know how it looks like. Once you do, it's much easier. So I don't think math is a science. I think it's religion. A religion, yeah, all the equations are like miracles. You take two numbers, and when you add them, they magically become one new number. No one can say how it happens. You either believe it or you don't. That's funny.
Yeah, we're related. You guys know that there's infinite numbers between 0 and 100.
Yes.
Uh, I don't know.
All right. Let's watch this pretty quick. Basically, the dot product multiplies the vectors together, then adds them together. That is what the inner product does. It multiplies and adds the text embeddings and the image patch embeddings. And if you don't know what an image patch embedding is, it's quite literally what it sounds like. It's literally a patch of an image. Where is it? This is an image patch. It's literally a patch of an image. So an image patch embedding is just an image. It's just the embeddings of each image.
Good night. Good.
Good night. Oh. Yeah. So basically how we could implement this paper is so first you have an image, then an image geometric prompt. This would then be fed into the encoder of SAM clip and the prompt encoder of the prompt encoder of SAM. This would then get fed into the three. Actually, I don't know if it's for SAM. I don't know if it's for clip. It could be something different for SAM. Yeah, it could be different. Let's go and figure that out. Proposed approach. Avalon. Are you with us?
I am. What section would you like me to pick up from?
proposed approach. Proposed approach.
Okay. In this section, we explain our multitask distillation approach for efficiently merging pre-trained VFMs. We start with a VFM as the base model, then transfer knowledge from other auxiliary VFMs to it with minimal forgetting. We'll assume that each VFM possesses a vision encoder and potentially other modality encoders, as well as a task-specific decoder heads. Our goal is to combine the vision encoders into a single backbone such that it can be used in conjunction with other modality encoders which remain frozen. To focus our exposition, we constrain our discussion to the specific case where SAM serves as the base VFM, while a clip model serves as the auxiliary VFM. This pair presents an intriguing combination, as both models have been successfully deployed in diverse tasks and exhibit complementary capabilities. SAM excels in localization and high-resolution image segmentation, but has limitations in semantic understanding. Conversely, CLIP offers a powerful image backbone for semantic understanding. We demonstrated by several probing experiments, as shown in Figure 4. Potentially, one could start with CLIP as the basic VFM and merge knowledge of SAM to it. However, existing pre-trained CLIP VIT models are inefficient in dealing with high-resolution images that are used for SAM training. Hence, we choose SAM as the base model and inherit it to bit DET structure that can process high-resolution inputs efficiently. We assume access to limited subsets of datasets or their proxies used to train the base and auxiliary VFMs, which function as memory replay in our CL setup. They're denoted as DSAM and DCLIP, respectively, with details provided in 4.1. We employ a multi-head architecture as illustrated in Figure 2. Our base VFM SAM has an image encoder, ENC SAM, a prompt encoder SAM, and a light mask decoder SAM. The auxiliary to VFM CLIP has an image encoder CLIP, a text encoder CLIP. Our goal is to merge both the image encoders to a single backbone called an encoder SAM CLIP, which is initialized by encoder SAM. Further, we consider lightweight heads corresponding to each VFM, namely head SAM and head CLIP. Head SAM is initialized with masks decoder SAM, and head CLIP is initialized with random weights, since CLIP does not come with a head that we can deploy. We deploy other modality encoders, that is prompt encoder SAM and text encoder SAM, with no change, that is frozen. As a baseline merging approach, we perform knowledge distillation on DCLIP using a cosine distillation loss. So the loss for CLIP equals the expected value of X approximately equal to DCLIP, all for 1/phi pooling for the head CLIP, for the encoded for the SAM CLIP for X, transpose times the encoder CLIP X, where phi pooling is a spatial pooling operator that gets patch level features from head CLIP and produces a normalized image level embedding. Yep.
You're cut off.
I thought I heard Kai has a question. I'll keep going.
So the base VFM SAM has an image encoder and a prompt encoder and a light mask. The auxiliary VFM CLIP has an image encoder CLIP and a text encoder CLIP. Our goal is to merge both image encoders to a single backbone called encoder SAM clip, which is initialized by encoder SAM. We consider lightweight heads corresponding to each VFM, namely head SAM and head clip. Head SAM is initialized with the mask decoder of SAM, and head clip is initialized with random weights, since clip does not come with a head that we can deploy. We deploy other modality encoders, prompt encoder, and text encoder with no change, frozen. They perform KDO. What is KD? On D clip.
Knowledge distillation.
Oh, that's right. On D clip, utilizing a cosine distillation loss. What would this look like? Cosine distillation loss. What does that mean exactly? So it's just a loss, a cosine applied to a loss. Huh?
Yes, I believe that's the case.
Okay. So the L, does the L mean loss?
The L is the loss.
So the loss of clip is equal to the E. I forgot what that is. E capital notation. What does that E stand for?
The E is the expectation.
The expectation.
The Wikipedia page. Expectation is the probable value for the function.
The probable value. Huh. So then they take the clip. 1 minus the max pooling or the theta. Is that theta? Phi. Is that phi?
Phi.
So pooling head clip with the encoder SAM clip combine X encoder clip, where pooling is a spatial pooling operator that gets patch level features from a head clip and produces an image level, a normalized image level embedding. Did you reach this, or am I?
Yes.
Okay. The pooling is a spatial pooling operator that gets patch level features from head clip and produces a normalized. And this set of parameters of both head clip and encoder SAM clip are learnable, while the clip encoder clip is a frozen and used as teacher. Basically, what the frozen and the trainable, what that means is like it's basically what it means. It's frozen. You can't train it. If you try to train it, the weights wouldn't work, and the trainable are like the weights can actually change and learn.
I think also that they're using frozen layers here helps prevent catastrophic forgetting.
Well, yeah, it does, but like you're also not learning anything at all. Would you rather not learn anything at all, or would you rather catastrophically forget things?
So what they are learning, but only a tiny bit at the output layer, where they learn the combined embedding of the clip and the SAM models. So they are learning, but they're not revising the inputs, namely the SAM model, which they then used to guide the clip model into a correct embedding for the combined one.
All right. Where'd you leave off?
Okay. While this infuses SAM with clip semantic abilities, it incurs at the cost of catastrophic forgetting of SAM's original capabilities. Further, we show that this training-free mitigative methods against catastrophic forgetting, such as WISE-FT, to be ineffective in our context of VFM merging, as demonstrated in section C. To address these challenges, we propose a rehearsal-based multitask distillation. This serves two primary goals: facilitate the efficient transfer of knowledge from the auxiliary VFM to the base model, and to preserve the original capabilities of the base model. Inspired by Kumar 2022, we consider a two-stage training, head probing and multitask distillation. An optional stage of resolution adaptation can be appended if the multiple heads are trained under different resolutions, which is the case of our experiment of merging SAM and CLIP. See section 4.1 about details of resolution adaptation. 1. Head probing. In this stage, we first freeze the image background encoder SAM clip and only train head clip with the loss in equation 1. Intuitively, with this approach, we first learn some reasonable values for parameters of head clip, which is initialized randomly before allowing any change in encoder SAM clip that is prone to forgetting. What was that?
V, can you go down? We're at head probing. I guess she's not with us. V has gone away. All right, let's keep going.
I'll keep going.
I'll record.
Would you like to cast? Okay. Multitask distillation. In this stage, we allow all heads, as well as our image encoder, to be learnable. We perform a multitask training on loss clip plus lambda loss SAM, with loss SAM equal to the expectation of x comma d, approximately equal to data SAM, times the loss of the functional distillation of head SAM for the encoder SAM clip for x and the prompt encoder SAM G and Z. That's the where X is the raw image, G is a geometric prompt, Z is the mask decoder SAM for the encoder SAM for X as a segmentation mask score produced by a frozen SAM teacher, and LFD refers to a linear combination of focal and dice used in the original SAM training adapted for distillation. We train on DSAM union with D-clip with a total loss of loss clip plus lambda loss SAM. During each training, each batch has some samples from D-clip and some from DSAM, which contribute to loss clip and loss SAM respectively. That is, samples from clip dataset do not contribute to SAM loss and vice versa. To encourage less forgetting, we use an order of magnitude smaller learning rate for the parameters of encoder SAM clip and head SAM compared to head clip at this stage.
So theirs is slightly below data comp on ImageNet. It does only 41 million parameters. That's pretty good.
Yeah, this model's tiny.
This is ImageNet v2. Clip data comp 1 billion. Wow, that's insane. Data comp 1 billion does better than Lion 2 billion. Probably because of better captions and stuff.
And considering how much smaller SAMClip is compared to DataComp, it does really extraordinarily well.
It does. The multitask distillation. So all heads. We perform multitask training on the clip and SAM with SAM. Each batch has samples from dclip and some form dsam, which contribute to lclip and lsam respectively. Samples from clip do not contribute. All right, let's keep going. Experiments, implementation details.
Okay. Model architecture. We employ the VIT B16 version of Segment Anything Model SAM as our base architecture, comprising 12 transformer layers. To integrate clip capabilities, we append a lightweight clip head consisting of 3 transformer layers to the SAM backbone. The patch token outputs from this clip head undergo a pooling layer to produce an image-level embedding akin to the role of the CLS token output in VIT models. We adopt max pooling since we observe that it can lead to better zero-shot classification and semantic segmentation performance of SAMClip than average pooling. It is noteworthy that max pooling has been found to be able to encourage the learning of spatial visual features. With the pooling label, the clip head can output an embedding for the whole image, which can be aligned with the text embedding, just like the original clip model. Dataset preparation. For the clip distillation, we merge images from several datasets: CC3M, CC12M, YFCC15M, a curated set, a subset of YFCC100M by OpenAI, and ImageNet21K. This forms our dclip containing 40.6 million unlabeled images. For the SAM self-distillation, we sample approximately 6% subset from the SA1 billion set to form DSAM, which originally comprises 11 million images and 1.1 billion masks. We randomly select 1% of dclip and dsam as validation sets. Overall, we have 40.8 million images for training, which we term as merged 41M in this work. Training. As we discussed in section 3, the training is conducted in 2 phases to optimize convergence in a probing, then full fine-tuning style. The first stage of clip head probing takes 20 epochs on dclip while the backbone is kept frozen. Here, the teacher model is OpenClip VITL14, trained on the DataComp 1B dataset. In the second stage, 16 epochs, we unfreeze the backbone encoder SAMClip and proceed with joint fine-tuning together with headclip and headsam, incorporating both clip and SAM distillation losses at the ratio of 1 to 10. The original SAM BitB model serves as the teacher in SAM loss. Further, the learning rates applied to encoder SAM clip and head SAM are 10 times smaller than that of head clip in order to reduce the forgetting of the original SAM abilities. Besides, we adopt a mixed input resolution strategy for training. A notable difference between SAM and CLIP is their pre-training resolution. SAM is trained and works best on 1024 pixel resolution, while often lower resolutions, 224, 336, 448, are adopted for CLIP training and inference. Hence, we employ variable resolutions of 224, 48 pix for the CLIP distillation via the variable bench sampler approach of Meta et al. 2022, while SAM distillation uses a 1024 pixel resolution in accordance with SAM's original training guidelines. In every optimization step, we form a batch of 2048 images from dclip and 32 images, each with 32 mask annotations from dsam, and perform training in a multitask fashion. Let's take a look at figure 3 now.
This is really interesting. So this is the input image. It's a nice doggies. Then wait, the ground truth. So this is like the actual segmented version of the image. You see the horse. Everything is precise. The doggies are also pretty perfect. The legs, the head, the ears. Now, if we move on, we see the clip head prediction. So you could obviously see it's a lot more messy. Not as precise around the edges. It still gets it right for the most part, but it's like pretty messy. And then if we go to the horse is extremely messy. Takes out the background trailer, the pants, the I don't know, the saddle is wrong. The legs is wrong. And then there's some areas just completely outside the horse. And then that's the clip head prediction. And then this is the SAM head. Point prompts. Dog background. You can see it's pretty precise, but the thing is around the neck there's like some dots. That's probably about it, but other than that it's pretty precise. There's some little dots. But then the horse, we can see the horse is much more precise. The lasso, the saddle, the legs. Maybe not the leg in the back because it blends in with the background, but you can also see the person.
I think the stars are the kernel for the segments.
So the stars are basically like the prompts. So you give it a prompt. You give it a prompt and it'll segment it. Are you saying something, Zach?
Oh, yeah. I wonder something like this is something that Nemo would be looking for his face recognition. I guess the problem there isn't necessarily recognition, but
Evelyn, can you mute for a sec? What were you saying?
I guess the problem there wouldn't be recognition, but like determining whether it's spoofed or not.
Yeah.
Like AI could generate 3D photorealistic renderings of people that are indistinguishable from them. So that'd be more like that'd probably not work with this.
Maybe there could be facial recognition segmented. I don't know if that is true. I don't know if that exists. Maybe. How can I segment? Maybe. I mean, yeah, something like this would work to analyze who the person is. Their facial features, but also have to match. Yeah, this could probably be a good facial recognition model if it was trained for facial recognition tasks. But it isn't for the most part, so it would have to be retrained on a facial recognition data set. But yeah, this would probably be a good facial recognition model. Oh, that's a pretty good idea, Zach.
Thanks.
All right, let's keep going.
Okay. Resolution, adaptation, covered that. Zero-shot evaluation clip task. Zero-shot image classification. To examine the clip-related capabilities of SAMClip, we evaluate with the zero-shot image classification on ImageNet, ImageNet v2, and Places 365 under the image resolution of 224x. We use the text templates as Radford 2021, using the textual embeddings from the text encoder SAMClip, which is kept frozen from our clip teacher to perform zero-shot classification without any fine-tuning. The evaluation results are presented in Table 1. Employing VIP architecture, our model achieves zero-shot accuracy comparable to the state-of-the-art clip VIP models pre-trained on Leon 2B and Datacomp 1B, both released by Ilarco 2021, over the 3 datasets. These results validate the efficacy of our merging approach in inheriting clips capabilities. Note, we observe that SAMClip can benefit from 336 pixel resolution for zero-shot image classification, while the baseline clip models do not. The evaluation results of SAMClip under 336 pixels are provided in Appendix A and also incorporated into the diagram in Figure 1. Any questions about that?
No. But something I have noticed is that the vidth of SAM is much better than the vidth of clip for some reason. Like it's significantly much better because the resolutions are much higher.
Yes, clip was trained. The original clip was trained on pretty small images. I'm optimistic that the meta clip might be more useful. Perhaps it has been trained on larger images.
Yeah, perhaps.
No matter how large the image, no matter how large the training data is, if we don't have a quality data, then the model is nothing.
That's a good
At
finding.
the end of the day, the quality of the data matters the most.
Mm-hmm.
I agree.
Right?
Actually, I'd say the model architecture is more important than data. Because the model architecture, if you have a good enough model architecture, you wouldn't even need to find a data set. It would make one for itself. That's what RoboCat does. That's why it's insane.
Oh, did you watch the RoboCop movie?
RoboCats, not RoboCop.
Oh shit, my bad.
But that's a pretty good movie. Robots.
Yeah.
I don't think I read the RoboCat paper.
It's really insane.
Yeah.
That's where I got the idea for the hive mind robotic model that can pilot an arbitrary amount of robotic models and communicate instructions to them. That's the paper. Basically, the model there is multimodal and it's multi-embodiment, and it also generates its own training data. So, like, imagine literally generating like billions of like images of like robotic arms doing complex tasks. Then it just trains itself. That's it. Like it's completely self-sustaining without human intervention. It's really good.
That's amazing. I'm going to keep going.
All right, let's analyze this this thing. Representation learning class.
Okay. This has the blue segment is SAM, the red segment is CLIP, and the green segment is SAM CLIP. CLIP is good on all tasks comparatively to SAM, and SAM CLIP is a small improvement on about half of the tasks. Head probing evaluation of each vision backbone for classification and semantic segmentation tasks. SAM CLIP learns richer visual features compared to SAM and CLIP. In table 4, the linear probing evaluations on image classifications, datasets with VIT-B models, and the models are SAM, CLIP on Datacomp 1B, CLIP on Layon 2B, and SAM CLIP. The linear probing for ImageNet has CLIP Datacomp 1B as the best, and the linear probing on Places 365 has SAM CLIP as the best. And table 5, composing both CLIP and SAM heads of SAM CLIP for zero-shot semantic segmentation on Pascal VOC. We've got a method of CLIP head only at 448 pixels with a MIOU, and I don't know what that means, of 60.6, and CLIP plus SAM heads at 1024 pixels has a result of 66, which is the best. Composing both SAM and CLIP and SAM heads for better segmentation. Given that SAM CLIP is a multitask model with SAM and CLIP heads, one would naturally ask if the two heads can work together towards better performance on some tasks. Here, we showcase that a simple composition of CLIP and SAM heads can lead to better zero-shot semantic segmentation. Specifically, we resize the input image to 1024 pixels and pass it through encoder SAM CLIP and use the CLIP head to generate low-resolution mask prediction 32 by 32 using text prompts. Then we can generate some point prompts from the mask prediction, importance sampling based on the mask prediction confidence, and pass the mask prediction and point prompts together to the prompt encoder module as geometric prompts. Finally, HeadSAM takes embeddings from both the prompt encoder and the image encoder to generate high-resolution mask predictions, 256, 256, as shown in Figure 2 right. Examples of this pipeline are shown in Figure 3. One can clearly observe that the refined segmentation by the SAM head is more fine-grained. The implementation details are in Appendix B. Note that this pipeline requires only one forward pass on encoder SAM clip with 1024 pixel resolution. For fair comparison, in Table 1 and Figure 1, we report SAM clip zero-shot segmentation performance with 448 pixel resolution using head clip only. Using our high-resolution pipeline, we've obtained further gain in zero-shot semantic segmentation as shown in Table 5. Would you like me to go through any of the appendices?
The conclusion, please.
Okay. In this work, we discussed merging publicly available vision foundation models as digested sources of visual knowledge into a single unified architecture. We proposed a simple and efficient recipe based on multitask distillation and memory rehearsal. Specifically, we instantiated our proposed approach to merge SAM and CLIP vision foundation models and introduced SAM-CLIP. SAM and CLIP have complementary vision capabilities. One is good on spatial understanding, while the other excels on semantic understanding of images. We demonstrate multiple benefits as a result of our proposed approach. One, we obtain a single vision backbone with minimal forgetting of zero-shot capabilities of the original models, suitable for edge device deployment. We demonstrate the merged model produces richer representations usable for more diverse downstream tasks when compared to original models in a head-probing evaluation setup. And three, the merged model demonstrates synergistic new zero-shot capability thanks to complementary inherited skills from the parent models. Specifically, we show that SAM-CLIP obtains state-of-the-art performance on zero-shot semantic segmentation task by combining semantic understanding of CLIP and localization knowledge of SAM. This is really exciting that they're combining these relatively distinct models in a way which allows them to gain synergistic benefits from both and is so much smaller than the originals. This is kind of...
Yeah, this is nice.
Interesting.
Yeah, I think a lot of this multimodal research has been happening recently. It's just people combining different encoders and things, and then they're reaching new state-of-the-art benchmarks. Basically, this is like a mini swarm. This is like a mini swarm of like models, and they're basically like collaborating. So I definitely think this is a very good paper. And we're not done. Let's finish the appendix so we can.
Okay, I'll see which one looks good to read.
Yeah.
Appendix A are more experimental details. Appendix B are the inference experiments. C is the weight averaging. D are the limitations. A, more experimental details. Software. They use PyTorch, CVNets, and the evaluation code for instant segmentation relies on the publicly released code bases from Krylov 2023 and Lee 2022b. They used servers with 8 times A100 GPUs, which is a relatively small cluster. For training our models, we employed multi-node training across 4 8 times A100 servers, which is slightly larger. The local batch size per server is 1/4 of the global batch size.
Clip head structure?
Essentially just... Clip head structure. What was that?
Clip head structure.
No, they're just splitting the data. They're just splitting the data across 4 servers.
Yeah. That is the reasonable thing to do.
You think it's reasonable or unreasonable?
No, super unreasonable. They should just have everything on one CPU.
So they've got 4 servers, each with 8 GPUs, and they are using a local batch size per server of 1/4 of the global batch size.
Yeah. Yes, a project like this wouldn't require too many GPUs.
Yeah, it's definitely not a big problem, which is again very encouraging for swarm models. That once you have a well-trained base model, the fine-tuning gets easier and easier.
Yeah, absolutely. All right,
I'll go on to the clip head structure.
Yeah.
Clip. We initialized each transformer layer of the clip head using parameters from the last transformer layer of SAM fit B, as we found this approach to expedite training compared to random initialization. Following the implementation of clip convex next in ELARCO 2021, the only open clip model that uses a pooling layer instead of a CLS token, we incorporated a layer norm layer subsequent to the pooling layer. After applying a layer norm, we use a shallow MLP with 2 hidden layers to project the features into the text embedding space, consistent with the approach in Rosenthal 2022. Hyperparameters. We employ Atom W optimizers with a learning rate of 8 to the 10 to the negative 4, consistent with SAM training. During the first training stage, head probing, for 20 epochs. This rate is reduced to 4 times 10 to the negative 5 during the second stage, joint distillation, for 16 epochs. It should be noted that we apply a learning rate multiplier of 0.1 to the backbone and SAM head in the second stage to mitigate forgetting. The learning rate in the resolution adaptation stage 3 epochs remains the same as in the first stage. The global image bounce size for clip distillation is 2048, and for SAM's distillation is 32. That is 32 images from the SA1B dataset. In the latter case, we randomly sample 32 masks for each image. And the image resolution for zero-shot classification. In Table 1, we report the evaluation results for both SAM clip and clip models using 224-pixel image resolution. However, we found that SAM clip benefits from the 336-pixel resolution, where the performance of clip models deteriorates. They exhibit worse accuracy. The 336-pixel results for SAM clip are incorporated into the diagram in Figure 1. And the comparison between the 224 and 336-pixel resolutions is in Table 6, where it shows that 224 and is worse on ImageNet, is the same on ImageNet v2, and is slightly worse on Places 365, whereas a 336px is better or equal on all 3 tasks. The next section is inference experiments. Does anybody have any questions about the experimental detail?
Nope.
Okay. Inference experiments. Clip and SAM tasks. The inference process for zero-shot classification is identical to that of the original clip. The evaluation of zero-shot instance segmentation also exactly follows the protocol outlined in Krylov et al. 2023. The image resolutions for classification and instance segmentations are set at 224 and 1024 pixels, respectively. For the zero-shot semantic segmentation, we largely adhere to the practices outlined by Rashnagati et al. 2023. We insert the class names into 80 prompt templates created by Radford et al. 2021 and obtained text embeddings using the text encoder. Next, we compute the cosine similarity between each text embedding and the corresponding patch feature, the output of the clip head. The class with the highest cosine similarity is selected as the predicted class for each patch. We then resize the patch class predictions to match the original image dimensions and calculate MIOU scores. The evaluation resolution is maintained at 448 pixels for fair comparison with previous methods. And then Figure 5, the WISE FT to a clip distilled SAM VIT-B model. The red dashed line marks the performance of the clip teacher model. The zero-shot accuracy of the teacher remains very good. The SAM clip improves as the alpha goes up. And on the zero-shot image segmentation, MAP, the SAM clip score goes down as the alpha goes up. Composing clip and SAM heads. To combine both clip and SAM heads for zero-shot semantic segmentation, we first resize the image to 1024 pics and run the clip head to obtain mask predictions, that is, logits for each class. Subsequently, we pass the mask prediction corresponding to each class to the prompt encoder, along with 1 to 3 auto-generated points. These points are randomly sampled from pixels where the mask prediction logics exceed a specific threshold. For Pascal VOC, we find that a threshold of 0.5 is generally sufficient. The output from the prompt encoder is then fed to the SAM head, that is the mask decoder, along with the patch token outputs from the VIT backbone. Finally, the mask decoder produces fine-grained mask prediction logits for each class, and we designate the class with the highest logit value as the predicted class for each pixel. Any questions? Okay, the weight averaging. It's a straightforward post-processing method proven to mitigate forgetting across a variety of fine-tuning tasks. Specifically, WiseFT proposes linearly interpolating the pre-trained and fine-tuned parameters using a coefficient alpha. In this study, we explore the application of YSTFT in our setup. We focus exclusively on clip distillation applied to SAM VIT-B, serving as the student model, with a clip VIT-B16 model acting as the teacher model. The model is trained on ImageNet 21K for 20 epochs. It's evident that the fine-tuned student model, alpha equals 1, gains zero-shot classification capabilities at the expense of forgetting its original zero-shot instance segmentation abilities. Upon applying WiseFT to the fine-tuned model, we observe an inherent trade-off between learning and forgetting. Notably, no optimal point exists where both high classification accuracy, greater than 60% at ImageNet, and a high MAP, greater than 35 MAP on COCO, are achieved simultaneously. Limitations. Our proposed method for merging existing foundational vision models could inherit the limitations of the original models. Specifically, our approach may carry over limitations from both the original SAM and CLIP models, including data distribution biases. We have not assessed the robustness and fairness of our method in this work. And that is the end.
I think this paper is really good. I think it's a testament to what happens when you integrate two things together in a pretty good way. I definitely think there's going to be a lot more models like this. Kind of like beginning to form a swarm. I don't know if 2 agents is a swarm. Maybe it is. But as soon as we start seeing 3 or more models combine, things are going to get interesting. especially in a way that's also logically coherent. The way that they fuse the models here, the way that they fuse the models here is pretty good. Yeah, that's what I think.
I agree. This is a very good paper. I'm particularly excited by how straightforward and simple the training was, how little training effort it took to combine the two models, and how tiny the final model was. This is a very exciting direction of research for combining more foundation models.
Yeah.
Does anybody else want to chime in?
Yes, more is better. More for sure. Better. For sure. I just wish it was open source so we could start fine tuning it. I guess we've got everything we need here to implement it ourselves.
There was actually just another vision model that came out called, what is it called? ConvNets Match Vision Transformers at Scale. And yes, Zach. Yeah, I think this could definitely be implemented now. I mean, the separate components like the vision encoder and the prompt encoder and all that stuff is already in the OpenAI repos for Clip, and it's also in the you could find the code in the OpenAI Clip repo and the segment anything repo by Facebook Research. Both of these repos, like, you would just copy the code and then make the integrations between the new or the modalities and the encoders. I'm gonna definitely look into a lot more research. I'm gonna conduct a lot more research into the vision encoder of SAM. I think it's really good, and it could be a kind of like a benchmark for future multimodality models that are high performance. So that's what I think.
Given exciting times. Thank you for picking a good paper, Kai. Thanks for showing up, Zach and V. And I hope you all have a lovely rest of your evening.
You too.
Thanks for reading on them.
Good night.